Hello, hello everyone. My name is Manisha Singh and I have been working at MD Anderson Cancer Center for over 15 years, focusing on immunotherapy for solid tumor. Today I am going to talk about the role of interleukin-1 in tumor microenvironment and how interleukin-1 suppresses the anti-tumor immunity. I will start with melanoma and then showing some data on pancreatic cancer. So let me tell you how the interleukin-1 story began. During my work on melanoma, I found only a small tumor respond to immunotherapy, but large tumor never respond to immunotherapy. So you can see here when tumor were less than 50 mm square, it responded to immunotherapy, either monotherapy or combination therapy. But when tumor larger than this size, around 50 mm square, or you can say 40 to 50 mm square, these tumors never responded to immunotherapy. So we decided to find out the reason why large tumor don't respond to immunotherapy. And we performed transcriptome and also did multiplex cytokine or chemokine assay. And from bulk RNA-seq data, we found a smaller tumor had higher number of activated antigen-presenting cell, NK cells, T lymphocytes, and large tumor had oncogenes and also MDACC related genes. And in cytokines, we found more interferon gamma, IP10, RANTES in small tumor, and IL-4 in large tumor. So you can see here tumor microenvironment shift from immune active to immune suppressive to small tumor to large tumor. So these all are Th1 cytokines and this is Th2 cytokines. So then next we did cytof to determine the difference between a small tumor and large tumor, and we found PMN MDACC interleukin 1 alpha Treg increased when tumor size increased, and interleukin 12 activated CD8 T cells and CD4 T cell decreased when tumor size increased. And in lytic C cells, so lytic C monocytes induce interleukin 1 alpha in large tumor, and the same kind of cells, I mean the lytic C positive monocyte induce interleukin 12 in a small tumor. So responded tumor had more interleukin 12 and non-responded tumor had more interleukin 1 alpha, and both interleukin 1 alpha produced by lytic C monocytes. So we hypothesized that interleukin 1 alpha signaling drive Tregs and PMN MDACC in tumor microenvironment. Those induce immune suppression and resistance to immunotherapy. This is the first experiment. We injected melanoma in interleukin 1 receptor knockout and wild type and found melanoma grows slowly in interleukin 1 receptor knockout than wild type. Next we perform transcriptomic. So this is bulk RNA-seq data, and you can see here interleukin-1 receptor blockade antibody induce more CD8 T cells, and CD8 T cells, or you can say T cell related cytokines like interleukin 2, and also when we block interleukin 1 pathway, there are more interleukin 12, chemokines CXCL10, CXCL11. However, less CXCL1. So the CXCL1 is the main chemokines that can attract MDACC. So when we block interleukin 1 pathway, there is less CXCL1 chemokines, and also low number of Ly6C. So this is also Ly6C like MDACC. So previously we reported that CD40 agonists significantly suppress melanoma growth and induce anti-tumor immunity. So this is the actually the CD40 agonist. Here we use CD40 ligand, and you can see here it's pretty effective against melanoma and also induce anti-tumor immunity. We thought to combine interleukin 1 receptor antibody with CD40 agonist, and our surprised we found synergistic effect of we can say like the combination is better than the monotherapy. So when we block interleukin 1 pathway and give CD40 agonist, this combination was better than CD40 agonist alone. And also this combination induce more tumor specific CD8 T cells. So we actually determine the region of this synergistic effect and found CD40 agonist induce interleukin 1 alpha in tumor and also induce PMN MDACC in tumor. Next, we found when we block interleukin 1 pathway, there is a less PMN MDACC in tumor. So blockade of interleukin 1 pathway reduce the number of CD40 agonist induced PMN MDACC. And to validate that PMN MDACC is the main population that are suppressing the anti-tumor immunity through interleukin 1, we adaptive transfer of PMN MDACC in the mice and found these adaptive transfer of PMN MDACC abrogate the effect of interleukin 1 pathway blockade. So we conclude that presence of interleukin 1 alpha in melanoma makes the disease resistant to immunotherapy. Interleukin 1 pathway blockade enhance the efficacy of CD40 agonist therapy, and interleukin 1 pathway blockade improve response to immunotherapy through elimination of PMN MDACC. So actually, because we found CD40 agonist and interleukin 1 blockade is really good combination, and pancreatic tumor respond to CD40 agonist. However, CD40 agonist also cause liver damage in pancreatic cancer patient when we treat with CD40 agonist, and also the CD40 agonist monotherapy is not pretty effective. It's like after some time, like less than 50% patient responded to CD40 agonist, and after some time this patient developed resistance. So we choose pancreatic cancer model to find out whether the blockade of interleukin-1 with CD40 agonists is effective against pancreatic cancer. So you can see here is we just block the interleukin-1 pathway and compare with isotype control, and here is significantly tumor suppression with anti-interleukin-1 receptor blockade group. Similarly to melanoma, we found that CD40 agonists induced PMN MDACC in tumor, and blocking of interleukin-1 pathway with CD40 agonists reduce the number of PMN MDACC in tumor. And then we found anti-interleukin-1 receptor antibody enhance the efficacy of CD40 agonist. It's not pretty powerful like melanoma, but still there is more, I would say, more survival than alone CD40 agonist. So it enhances the efficacy of the CD40 agonist. We have only 5 mice per group, so it is actually initial experiment. So let's see. We found when we block interleukin-1 with CD40 agonist, the combination therapy downregulated many pathways like HIF1 alpha signaling pathway, NF-kappa B signaling pathway, and also TS17 signaling pathway. And these all pathways associated with tumor growth or suppression of the anti-tumor immunity. And blockade of interleukin-1 suppress these all pathways. Also, interleukin-1 pathway blockade with or without CD40 agonist treatment enhance activated T cells in pancreatic cancer. So you can see the all activated T cells molecules here like granzyme, CXCL10, STAT1, interferon gamma, CXCL11 is more in combination group than alone CD40 agonist. Also more when we compare alone interleukin-1 and no toxin. So this is the interleukin-1 alone, and here is no treatment. Also, it enhances interferon gamma response. The combination therapy enhances interferon gamma response and reduce interleukin-2 state 5 signaling. So these are hallmark pathway. So as I said before, that CD40 agonists cause toxicity and liver damage. So you can see here we actually analyzed two liver enzyme, AST and ALT. So this is serum AST and serum ALT, and we found blocking of this is a combination therapy, means the anti-interleukin 1 receptor and CD40 agonist here and here. So when we block interleukin 1 pathway with CD40 agonist, the AST and also the ALT level were reduced in serum. So that means it also reducing the toxicity of the CD40 agonist. So conclusion is that, like in pancreatic cancer, blocking of the interleukin 1 pathway enhancing the efficacy of CD40 agonist and reducing the toxicity of CD40 agonist. So here I try to summarize the anti-tumor immunity part. So activation of NF-kappa B pathway through CD40 agonists induce immunotherapy driven IL-1 production by inflammatory monocytes. In response to IL-1, interleukin 1 receptor expressing monocytes and macrophages produce PMN MDACC recruiting chemokines like CXCL1, CXCL2, CXCL5. And these chemokines recruit PMN MDACC in tumor, and these cells MDACC actually suppress anti-tumor immunity. When we block interleukin 1 pathway by anti-interleukin 1 receptor antibody, then there are more anti-tumor immunity. So I thank to all my mentor and collaborators, also my postdoc, and here my award, and thank you so much everyone, and I am happy to take any question. Thanks.